Today we are beginning chapter 14, which is the last chapter of the syllabus and the text. And hopefully we'll be wrapping this up in a couple of classes. We'll be done with the chemistry syllabus as well. We recently completed the physics syllabus. The chapter is titled Experimental Techniques and Chemical Analysis. And since you're seeing me using the text, this is mostly reading and stuff we need to know. Now, we won't be doing actual practicals in the lab, and of course, this is an online class. So it's more about theoretically knowing how we do things, how things are done. So the first thing we're starting off with is getting to know the apparatus used for measurement in chemistry. So scientists find out about the nature of materials by carrying out experiments in the laboratory. Many of these experiments require apparatus, right? So dishes, well, not just dishes, but things that are used in experiments, such that you have used in your study of chemistry to date. A knowledge and understanding of the use of the scientific apparatus is required for successful experimentation and investigations. In an experiment, you will first have to decide on the measurements to be made and then collect together the apparatus and materials required. The quantities you will need to measure most often in a chemistry laboratory will be temperature, mass, volume of liquids, as well as gases, and time. There will be advantages and disadvantages of each piece or method of apparatus, like my method or piece of apparatus. So when you choose which to use, you will have to use your knowledge of the apparatus to decide if it will be suitable. Things you need to consider, right? What apparatus should you use to measure each of these? For example, it sounds silly, but you would not use a thermometer to measure the timing of a particular rate of reaction. Right? Which piece of apparatus is most suitable for the task in hand? For example, you would not use a large gas syringe to measure out 10 centimeter cube of liquid. You would use a small measuring cylinder because it gives you a more accurate measurement of the volume and it is easier to use. Just because something is used to measure volume doesn't mean you pick out anything. You need, even in that, you need to be thoughtful about, whether I'm going to use a measuring cylinder or a gas syringe or a beaker or a conical flask or pipette or burette or something. How do you use the piece of apparatus correctly? So you selected it, but then how do you use it? Before you use a piece of apparatus, be sure you know how to use it properly. You need to be safe in your working habits and also to ensure you use good techniques, for example, measuring volumes of solutions carefully, so that you make and record measurements accurately. If necessary, ask your teacher before you use a particular piece of apparatus if it is unfamiliar to you. Now, talking about some of them, for example, for the measurement of time, experiments involving rates of reactions will require the use of an accurate stopwatch, one that measures to a hundredth of a second, right? Which we call split second. The units of time are hours, minutes, and seconds. And that's it. Right? Then measuring a temperature, obviously we're going to be using a thermometer. The most commonly used thermometers in a laboratory are alcohol in glass. Mercury in glass thermometers can be used but should be handled with care, with great care. The mercury inside them is poisonous and should not be handled if a thermometer breaks. The units of temperature are those of the Celsius scale. This scale is based on the temperature at which water freezes and boils. That is, the freezing point of water is 0 degrees centigrade and the boiling point of water is 100 degrees centigrade. The usual thermometer used is that shown in figure 14.2. So we saw that up there. We can go back and take a look at it again. So that thing. which measures accurately between -10 degrees and 110 degrees centigrade at 1 degree centigrade intervals. It may also be possible to read the thermometer to the nearest 0.5 degrees centigrade if the reading is between two of the scale marks. When reading the thermometer, always ensure that your eye is at the same level as the liquid meniscus in the thermometer to ensure that there are no parallax effects. So explaining this here, this is something we've covered in physics in chapter 1, way in the beginning. The meniscus is the way the liquid curves at the edge of the capillary in which the liquid is held in the thermometer, right? So some liquids, they curve up, some liquids curve downwards, right? So some may be convex, some may be concave. So we need to read the level of the meniscus, right? If it is convex, then we read the upper part of the meniscus over here. If it is concave, which they haven't shown, we read the lower edge of the meniscus if it is coming down, if in case it's coming down, right? And so your eye should be at the correct level. So over here, if we count, right, 10, 15, and then one mark, that's 16, another mark, that's 17, and it's between 17 and 18. So we can, as they mentioned, right, we can read it to the nearest 0.5. And so because it's more than 17 and less than 18, we can say, okay, fine, it's around 17.5 degrees centigrade. Similarly, over here, right, it's 0. And we count the number of markings. So we've got 1, 2, and 3, about 3 degrees centigrade, right? It's slightly above 3, not whole, like not like a whole above 3. You could argue that it's 3.5, or you could say, well, it's not, enough above 3 that you would call it 3.5. So let's go with 3. Right. Then measuring mass. There are many different electronic balances which can be used. The precision of an electronic balance is the size of the smallest mass that can be measured on the scale setting you are using, which is usually 0.01 grams, 0.0101 grams. So the units for measuring mass are grams and kilograms, right? And a kilogram is 1,000 grams. When using an electronic balance, you should wait until the reading is steady before taking it also, right? If properly placed, there is no airflow, there's nothing else, you've tiered it properly. So when there's nothing on it and the surface is clean, you zero it, and then you put whatever you want to weigh. If it's in a container and like over here, it's in a beaker. So what you do is that you put the beaker on it, right? For example, and you want just the mass of the liquid in this case, and so you put the beaker on it, you tear it with the beaker, right? When you take it off, it will show a negative reading for the mass, and that's because the beaker is not on it, right? So you set it to 0 with the beaker on it. So now when you can try and put the beaker back on, it will show you a 0 reading. Then you fill the beaker up over here. I believe it's about 100 ml, if I can see this correctly, right? So whatever this liquid is, and so you put in 100 ml of whatever this is, and you put it back on the scale, and then you get the mass of the liquid on, which is 155.12 grams, right? And then you can go ahead and do whatever it is the experiment is. Then measuring volume. So there are a number of apparatus that can be used. So you've got a pipette over here. Pipettes are fixed volumes, and they have a mark up till where, for example, there's a mark over here where up till the point you should fill the liquid, and if it's up till that point, then the total volume in the pipette is, for example, 25 ml, as it says over here. Then this is the burette, right? So the 0 mark is at the top, and when you're emptying it, right, it's calibrated to 0.1 centimeter cube all the way down here till 50. This volume over here below the 50 is extra. You do not take that into account. So if it goes below 50, it's problematic, right? Because that is not a measured volume. And then you put a measuring cylinder, right? Which in this case, this one's up to 100 ml. So volumetric pipette, measuring cylinder, and burette are generally used in different experiments. So the pipette and burette are something that you come across in titration. The measuring cylinder is more general, right? Depending on how accurately you want to measure. So different experiments involving liquids will require one or other or all various measuring apparatus available for measuring volume. Right? For acid-based titrations, you definitely need the pipette and burette. A burette and a pipette are needed, but this technique is often used to test the strength or purity of an acid or an alkali. A titration involves the slow, careful addition of one solution, such as an acid of a known concentration from a burette, to a known volume of another solution, such as an alkali of unknown concentration held in the flask. So once again, a titration involves the slow, careful addition of one solution, such as an acid of a known concentration from a burette, to a known volume of another solution, such as an alkali of unknown concentration held in a flask. Right? And so I just recalled that we haven't covered the titration bit. We left from chapter 8, acids and bases. So that is something we'll definitely do to wrap up the syllabus. Since we started this, let's cover it first. Okay. The solution in the burette is known as the titrant. This addition of acid continues until the reaction reaches neutralization, which is indicated by a color change in an indicator. Right, so normally what you do is you add the acid to the burette and you use a pipette to measure out a volume of the alkali, right? And you could technically use a measuring cylinder to get 25 ml, for example, of the alkali, but the pipette is more accurate. And because it deals with moles and concentration and stuff, and so you want to be as accurate in your measurement of volume as you possibly can be. Right, and then indicators, you've talked about those in chapter 8. They're different ones, and so you add an indicator to the alkali, and when you're adding the acid, right, the closer it gets to the point of neutralization, the color will change. You start seeing a color change until it comes to the exact point where a color change occurs, and that is the exact point where neutralization of all of the alkali has been achieved by the acid. And so you note the volume of acid, the concentration of acid. You go and do your molar calculations, which again we'll take a look at. And you figure out what the concentration of the alkali was, and maybe how much mass of chemical was used to prepare the solution, etc. Okay. The known volume in the flask would require the use of a pipette. For example, in acid alkali titration, the acid would be the titrant, and that would go into the burette. A measuring cylinder, sometimes called a mixing or graduated cylinder, is a common piece of laboratory equipment used to measure the volume of a liquid. It has a narrow cylindrical shape. Each marked line on the graduated cylinder shows the amount of liquid that has been measured. The volume of a liquid is a measure of the amount of space that it takes up. The units of volume are liter, cubic decimeters and cubic centimeters, right? So something I told you when we were doing moles, 1 liter is 1 decimeter cube, right, which is 1,000 centimeter cube. And so they haven't given ml over here, milliliter, but 1 centimeter cube is 1 milliliter basically. But that's not what we deal with, because in science volumes are given as, at least chemistry, they're given as centimeter cube. Okay. However, some of the manufacturers of apparatus used for measuring volume use milliliters, and so I just told you that. When reading the volume using one of these pieces of apparatus, it is important to ensure that the apparatus is vertical and that your eye is level with the meniscus of the liquid being measured. So again, the parallax issue. The precision of the measurement will vary depending on the apparatus. For example, if the smallest scale division on the burette is 0.1 centimeter cube, the precision of any volume measured with the burette will be 0.1 centimeter cube, right? So that depends on how finely graduated the apparatus is. The smallest division of the instrument will tell you its precision. It may also be possible to read the burette to the nearest 0 point. So just like we did with the thermometer, right? If it's between 2 points, and so, right, to the nearest 0.05 centimeter cube, if the bottom meniscus is between divisions. So here is an example. For the thermometer, we saw the upper meniscus when the liquid in the thermometer had a convex shape, it was curved upwards. Here's an example of a convex meniscus, and so you do not read the upper edges. Okay, so you don't read from here where the liquid is touching the sides, right? You read the lower meniscus, so the lower edge of the curve, right? The lower point of the curve, the concave meniscus, right? And you look at it at eye level. And so in this case, you're starting at 30, 1, 2, 3, 4, and this big line is 35, and then 36. So it's just at 36. And so we can say that, oh, it's 36 centimeter cube. Now, one thing to keep in mind, right, in the case of the burette, is that the reading starts from the top. Over here, this is a measuring cylinder, the reading starting from the bottom. So as much as you fill it up, right, the higher the volume. In case of the burette, it's the opposite, right? So zeros over here, and then for example, this is what, 10, 20, this is 30, right? And so you have to keep that in mind, because the liquid is going down, it will go down, and right, it's easy when you're starting off, but when you use the same liquid, if for example, right, you've got enough left, and for example you're starting over here at 46 and you went up till 48.5, right? So this is 46, right? So it's increasing as you go down, and you started at 46 and you went till 48.5. And so the question is, what volume of liquid did you use? So what you do is you write down the initial volume, which is 46, then you write down the final volume, which is 48.5, and then the actual volume used will be 48.5 minus 46, which will give you 2.5. So what you actually used was 2.5 centimeter cube. So that is how you would use a burette. Burette. Something to keep in mind. And so they will give you illustrations of burettes in your ATP, or even, for example, in paper 2, and they'll ask you, oh well, what are the readings? Okay. Now we have measurement of volume of gases. So the volume of a gas can be measured with a gas syringe, This is used to measure the amount of gas collected in experiments. They have a maximum volume of 100 centimeter cube. All right, so there's a pipe that you'll attach over here going into the apparatus. And if you're collecting gas or gas is filling in, as the gas fills in, right, this is very, relatively easy to move the plunger of the syringe. And so as the gas fills in, it will push the plunger up, and it's starting from zero near the end over here where the nozzle is. And so as much gas is collected, you can take a reading. If we just take a look at this in close up, all right, so this is perhaps 5 centimeter cube of gas in this thing, if there's if you just want to read it. All right, so the smallest reading on this thing is 1 centimeter, 1 ml, right? 1 ml meaning 1 centimeter cube. So you could perhaps take a reading of 0.5 centimeter cube on this, right? And what the precision will be? The precision will be 1 centimeter cube, right? So for example, in certain reactions, the reaction rate can be followed by collecting volume of gas generated over time. So for example, you're adding a carbonate to an acid, right? And you're doing the experiment where you have a clump of carbonate versus powdered carbonate, right? And so you would expect the powdered carbonate to produce carbon dioxide more quickly as compared to the clump of carbonate. And so you're measuring that. And so the gas syringe is connected by a tube to the flask that is giving out the gas. So you've got the reaction going on over here. This is like a rubber stopper, a rubber bung, and it has space. So you insert that tube, it will be a glass tube most likely, and you connect that to the gas syringe. And the gas collects, and over here it's gone to, right, what's the volume that we're seeing over here? So to about 79, right, I guess.
Sir,
About, yes.
Sophia is in the waiting room. Please ask him to let her enter the class.
I cannot see her in the waiting room. She could, try and rejoin
Okay.
if you could message her.
Yeah, I can.
Here she is. Salam alaikum.
Walaikum assalam.
Okay, so that's about, the gas, and as the gas is collected during the reaction, the plunger is forced out and the volume can be read from the scale. So I'll explain that and you can see that. The gas syringe has a scale along the length that allows the volume of the gas collected to be measured. And yeah, the plunger moves and the volume gas can be measured given time as it increases, and a graph of volume against time can be plotted, and then it can be used to show the rate of reaction. Okay, so that's about different apparatus, right? And we're dealing with temperature and time and mass and volume of liquids and volume of gases. Next up are experimental techniques. So the first thing we're talking about is separating mixtures. So we're going to talk about separating mixtures. Zoom out to see the whole thing. And chromatography. Then you've got qualitative analysis, right, where you're identifying different stuff. And yeah. So let's talk about separating mixtures. I think I zoomed in a bit too much. Many mixtures contain useful substances mixed with unwanted material. To obtain the useful substances, chemists often have to separate them from the impurities. So, you know, different methods and of separation have been developed, particularly for separating compounds from complex mixtures. Which separation method they use depends on what's in the mixture and the properties of the substances present. It also depends on whether the substances to be separated are solids, liquids, or gases. So there's a mixture of a solid liquid. If a solid substance is added to a liquid, it may dissolve to form a solution. In this case, the solid is said to be soluble and is called a solute, and the liquid it has dissolved in is called the solvent. An example of this type of process is when you dissolve sugar in water, right, or in tea and coffee. Sometimes the solid does not dissolve in the liquid, right? This solid is said to be insoluble. For example, tea leaves do not dissolve in boiling water when tea is made from them, although the soluble material from which tea is made are seen to dissolve from them, right? So stuff from the tea leaves is extracted, which gives the color and the taste. The tea leaf itself physically does not dissolve, right? That's what they're talking about. And so when you want to separate a mixture of a solid and a liquid, the most common thing you can do is filtration. Right? A very crude way of doing that is when we use a tea strainer and to hold back the tea leaves and only get the tea extract. So that is in principle filtration. So it's a common separation technique used in chemistry laboratories throughout the world. It is used when a solid needs to be separated from a liquid. For example, sand can be separated from a mixture of water by filtering it through a filter paper. So in the lab, you're not going to be using a tea strainer. Right? This is the setup. So this is a retort stand, right? And this is a clamp, right? And it has this spring. It could be a spring. It could be tightened with a valve type thing. And so this is what's called a filter funnel, right? The glass object. And inside is a filter paper. So you fold it in a particular way and then you pour the liquid through it. And so what it's going to do is, you can see there's sand in here. Some of it is settled at the bottom, so that's not problematic. But there's also you can see the water is not clear. So there's sand particles in the water. And so you're pouring it through the filter paper in the funnel, and the filter paper should trap all the sand particles, and what you should be getting is only the water, right? And the caption says it is important when filtering not to overfill the filter paper. So you don't want to go it near the brim, and definitely not over, because if it goes over the brim, then the water will go from behind the filter paper and you'll get contaminated water again, right? So this is a process that requires patience, because the filtration is, depending on what you're doing, can be slow.
Sir, do we have to write the apparatus name as well?
Can I write it? Let me see if I can just. Right, I won't be able to write it as such. I can maybe try and annotate over here. But
Do we have to write the apparatus name in the exam?
do you have to? Well, in your paper 4, they will ask you what apparatus to use. So yes, you will need to know the names of the apparatus.
Okay.
Okay. All right. There will be definitely a question where you'll be asked to sort of set up an experiment. And so one thing that you need to set up an experiment is the apparatus.
Yeah.
Okay, the filter paper contains holes that, although too small to be seen, are large enough to allow the molecules of water through, but not the sand. It acts like a sieve. The sand gets trapped in the filter paper and the water passes through it. The sand is called the residue and the water is called the filtrate. So what you're collecting is called the filtrate, and what's left in the filter paper is called the residue. All right, so again, these are terms that you need to know as well as the names of the apparatus. So that's the most simple thing, good thing for you, Sobia. All of this is going further in both the IGCSE and the O level. All right, so no centrifugation. Decanting is pretty simple. All right, decanting is just like pouring the liquid out until being careful that no solid follows. So it's a pretty simple thing. They haven't included that. Centrifuging is also something that can be done, obviously. Then there's evaporation. So in the case of you've got salt dissolved in water. So if a solid has dissolved in a liquid, it cannot be separated by filtration because it's dissolved. If you try to filter it, the whole thing will filter out. So right, you'll get salt water in the filter. So you're not stopping anything in the filter paper. Even centrifuging, which we haven't talked about, right? It's not going to work. Right? Centrifuging is basically, when you have a suspension and the particles like that, you can't filter it. So even though it's not part of the syllabus, so what you do is you put the test tubes in the centrifuge. The name of the apparatus is the centrifuge, and it spins it around at very high speeds, which causes the heavier particles to settle at the bottom. So you can see the insoluble solids are thrown to the bottom, and so they collect at the bottom, and then the liquid separates to the top. And so when the centrifuge stops, if you don't disturb it, right, this is what you get. So this was a blood sample, right, and these are the blood cells and plasma at the bottom. It was heavier, and because of the spinning, the heavier particles settle at the bottom, and this is right everything else.
Okay.
Right, so that's something that you wouldn't have been able to separate using filtration. You can see a sample of blood like that, right? So this is blood before centrifuging it, and that's after. Okay. So what we can do is, right, for a solution, right, a solid is dissolved, and so the solution can be heated so that the liquid evaporates completely and leaves the solid behind. Now this heating is done slowly. It's not like boiling, right? So the liquid evaporates completely and leaves the solid behind. For example, the simplest way to obtain salt from its solution is by slow evaporation, as I mentioned, right? So again, the focus is, remember the difference between evaporation and boiling, right? Evaporation is that at the surface, particles gain energy, and so they're leaving the liquid. It hasn't reached boiling temperature. The whole liquid is not undergoing a change of state. And so we are doing evaporation and not boiling. We are not taking the liquid to its boiling point. We are not trying to convert the whole thing to its gaseous form. Eventually, we will get to that point, but we don't want to take it to its boiling point.
Okay.
So you may need to choose a suitable solvent to separate a mixture. For example, if one of the substances in a mixture is soluble in water, you could use water to dissolve the soluble substance. Right, so this is if you have a mixture, right, and you want to separate one particular solute and from the others, and they are specifically soluble in water, the others aren't. So right, what you can do is you can put water in, like you can put it in water, or you can add water to the sample, and you can stir it, and so what you'll find is a suspension. The suspension is everything that did not dissolve, so those are solid particles, and the one that you want did dissolve. You can't see it, but it did happen. Then you filter it, and so right, you have the residue which you don't want, and then the filtrate, which does contain the solid in the dissolved form in water, which you want to separate. Then you take it and you do slow evaporation and you get rid of the water, and so you'll have a solid left behind, which is the solid that you want. Right, so it's a two-step process in that case. Right, if there's more than one solid, solids in the mixture. If it's just a single solid, we can directly move to the evaporation part. Right, so you could use water to dissolve the soluble substance, filter the mixture to separate the insoluble substance, and then evaporate it to retrieve the soluble substance. Then there's crystallization. In many parts of the world, salt is obtained from seawater on a vast scale. This is done by using the heat of the sun to evaporate the water to leave a saturated solution of salt known as brine. A saturated solution is defined as one that contains the maximum concentration of a solute dissolved in the solvent. Okay, so for example, if you've ever tried it dissolving sugar or salt in water, and if the water is at room temperature and you put a certain amount of sugar in it and you stir it, it will dissolve, and then you put some more and then it dissolves, but it takes more time, and then there comes a point, third or the fourth time, where it stops dissolving no matter how much you stir it. And so at that point, the water has become, like, whatever volume of water you've used has become saturated. That means that volume of water cannot dissolve any more of the sugar that you're putting in. There are a number of factors that affect, how much, when it becomes saturated. So first of all is the volume, right? If you add more water, then it's no longer saturated, and so it will be able to take in more sugar. Also temperature. So if you heat it up, it will be able to dissolve more sugar than it was at room temperature, and so those affect solubility.
Okay.
It is important to be aware that solubility of a substance varies with temperature, as I just mentioned. So the maximum concentration will vary at different temperatures. The higher the temperature, the more it will be able to take solute. When the solution is saturated, the salt begins to crystallize and it is removed using large scoops. All right, so here you've got salt being obtained in the northeastern part of Brazil by the evaporation of seawater. Are you guys following along so far? So good?
Yes.
Hmm. Okay, then you've got something called simple distillation. This is used when you have two different liquids that you want to separate, and it basically depends on the difference in boiling points of those liquids. Right, so if you want to obtain the solvent from a solution, then the process is called distillation, right? If you've got two different liquids, or if you've got a solution, if you've got a solid in here as well, right? And what you want to collect is not the solid, but the liquid part, right? And so you want to be careful about it. And so what you do is distillation, right? This is the apparatus. So you've got the solution in here, you're providing heat, you're keeping track of the temperature because, right, you're evaporating it up to the boiling point or under it, and so as the liquid evaporates, it rises up, it travels over here through the side arm, right, where you have the distillating column, and you're passing water through it. So water's going in, water's coming out, and so the water is, even if it's at room temperature, it will be cooler comparatively as compared to the gaseous particles, the molecules of the liquid, and so when it comes into this part of the apparatus, it will cool down, it will condense, it will reform liquid, and then you can collect it over here in the flask. And so that collected liquid is called the distillate, right? Named after the process. So filtration, filtrate; distillation, distillate, right? And that's a real life, picture of fractional distillation being carried out. Well, not fractional distillation, just a simple distillation. Fractional distillation is different.
Yeah.
So water can be obtained from salt water using this method. So in this case, what we want to obtain is not the salt, but the water. So we use distillation, right? If it was the salt that we wanted, we would have used crystallization and evaporation. So we need to be careful as to which technique we want to use. Well, not crystallization, but right, crystallization will happen eventually with evaporation, but right, it depends on what we are trying to achieve. Okay, so the method that we select depends on what it is we are aiming for. We could have the same scenario, and as I mentioned, if we are aiming to get the salt, we're going to use evaporation. If you're aiming to collect the liquid, we're going to use simple distillation. The solution is heated in the flask until it boils. The steam rises into the Liebig condenser, that's what it's called. So, right, this thing over here. This thing here is called the Liebig condenser.
Also.
Where it condenses back to water, the salt is left behind in the flask. So you are getting the salt, right? Because the concept is the same as with evaporation. The water is being removed and the salt is left behind. But the difference over here is, again, we don't want the salt, we want the liquid. So in case of evaporation, right, in this case, what you're doing is you're not too concerned about water being lost. It's evaporating, it's you're losing it, you don't care, right? And so what you're concerned with is the salt being left behind, and that's why your setup is different. Whereas when you want the liquid, your setup is going to be something else.
Yeah.
Okay. Just give me a sec. All right. Now, next up is the scenario where, right, so far we are talking about separating a mixture of a solid and a liquid, right? I did mention separating different liquids using distillation, so that's something that can be done. Right, that's coming in later. There's also, simply just separating them this way. So I think I'll stop here. We'll continue with this the next time, and right, we'll talk about all of these and then the qualitative analysis, and yeah, hopefully wrap up in time. So I'll see
Yeah.
you guys for the rest of this in the next class, inshallah.
Inshallah. Okay.
All right.
Allah Hafiz.
Allah.